In this section, I'd like to talk about electrical circuits. I've been referring to circuits a couple of times in previous videos when I've talked about potential difference in the flow of electrons along a conductor. I sort of inferred about circuits. You have everyday experience with circuits, of course. You know, all of your electrical devices are a circuit. So let's kind of talk about what we mean by an electrical circuit. So a circuit, what we mean by that is just a circle. If you've ever had to flip the circuit breaker in your house or change a fuse in your car, you had to do that because the circuit was open. Okay, so in your house, when your electrician needs to do electrical work, they'll turn off the circuit breaker. They will open the circuit, making it so no electrons can flow through the circuit, no electricity can flow. In your car, for example, headlights go out, fuses blow. When the fuse blows, what you have is the fuse is a weak point in the circuit, by the way. And what happens is, if you ever change a fuse, you notice that the little metal piece in the fuse is broken in two, right? Creating an opening in the circuit. An open circuit is one in which electrons cannot flow through the circuit, through the entire system. So in order for electricity to flow, we need closed circuits or circles. So let's talk about that. To have a circuit, you need a couple of things. So for one, to have a circuit, conductors must pass from the voltage source, the battery in some cases, through all devices and back to the source. You'll notice that your battery connects on both ends. When you put a AA inside your flashlight or put a new car battery, and you notice you're connected on both ends. When you plug into the wall, you're connected on, you two prongs on your plug in the wall. If a circuit breaks at any point, electricity stops flowing through the entire circuit. Batteries, for example, batteries being the thing that gives you the force for the circuit, they don't create anything. All they do is push electrons out from one end and pull them in from the other end. The conductor is just there to is a source of electrons. So the electrons flow through the conductor. So the conductor's own electrons are flowing through the circuit. And if the circuit is, of course, open, no electrons flow, circuit's not complete. Switches, when you turn your lights on and off in your home, you are opening the circuit when you turn your lights off, and you are closing the circuit when you turn your lights on. So flipping the light switch to the on position, lights go on, you're letting electrons flow through the circuit. When you turn your switch off, you are making a break in that circuit, so the circuit is said to be open. Three components for a circuit. You need a conductor. You need something to be a source of electrons and allow those electrons to flow easily. I can connect a shoelace from one end of a battery to the other, but a shoelace made of cotton or whatever is not a conductor. It may be a line. You may be able to draw a straight line. It might be a closed circuit, but there is nothing to conduct the electrons. There is no ability for those electrons to conduct through that cotton, for example. Whereas a copper or brass or otherwise metal wire would allow electrons to flow easily through it. So the conductor is the source of electrons. It's also what allows the electrons to flow. The electromotive force is given by the source, right? So the battery, for example, right? A potential difference is all you need. So you need a difference in charge from one end of the circuit to the other, and that's going to either push or pull. It's both. It's either or both. It doesn't matter how you phrase it, but push, pull, or a combination of both. Electrons are pulled and pushed toward the positive charge. And then if you just wanted to. If your goal was to let electricity flow, to just have flowing electricity, then you only need a conductor and a source, right? A wire connected to both ends of a battery will conduct electricity, but what's the point, right? The point usually when we use, put a battery connected to something, usually the goal is to do something, right? To do work, to move something, to spin a motor, if it's like your hair dryer or a remote control car or your actual car's windows or windshield wipers. We want to turn a motor, we want We want to turn a light bulb on, right? We want to spin the drum on your washer or dryer, right? We need a device, okay? Devices offer resistance to the flow of electricity. The reason why your light bulb lights up is because think of the old light bulbs, the incandescent with the filament in them, as electrons flow through that tiny filament wire, you're cramming a bunch of electrons, through that, along the surface of that wire, and those electrons cannot all stay on the wire. So what happens is they jump off the wire and back onto the wire, and that releases light. And we see that light as your light bulb lighting up. You need a resistor. So we'll talk more later about stuff I just kind of said. But we need a resistor, something to do to apply work to, something to use, right? Okay. So in this circuit, for example, the conductor is the wire. The source, the electromotive force, source of electricity, source of charge, is the battery. You notice there's two ends of the battery. We don't care which one's positive or negative right now. And a resistive device, in this case 3 light bulbs. You'll take note that these light bulbs are wired in a way that we call wired in parallel, where they all are going to receive equal amperage, equal current flow, but they'll split the force up between the 3. So each light bulb would be the same brightness, but they wouldn't be as bright as if you had one light bulb connected. The advantage to a circuit like this is you can take out, for example, the middle light bulb, and the other 2 still work. The conducting wire is resistive. The longer your wire is and the smaller your wire is, the more resistance you have. So shorter length, bigger diameter gives you better conduction, less resistance. So with a water hose, for example, the flow in the water, the following 3 changes in the conductor increase electrical resistance primarily through adding friction. You take, for example, you take your water hose and you kink it, right? You create a crease in the hose, and now at that point, less water will move because you've added resistance, but the water speeds up, right? The flow is not as great, but the water speeds up because of the added resistance. So the garden hose is a good example of it shows these 3 things. So there are 2 general types of circuits. I mentioned parallel already, but let's go through these. So the first type is called series. All devices connected in a row, daisy-chained, one after the other along the same wire. The downside to that, if there is any upsides, but the downside to that is you lose one device, you lose them all, because losing one device is equivalent to flipping the switch to the off position, or it's equivalent to making a break in the circuit. An open circuit exists when one device burns out. This is, for example, what you had in the older Christmas lights, where you had a big chain of lights, and one light would go bad, and they would all go bad, and you'd have to sit there and find which bulb was the one that went bad by trying and replacing one bulb at a time. The newer kind of holiday lights that we have would be wired in a parallel series. So if your Christmas lights allow one to burn out and the rest of them to keep working, they're wired in parallel. Parallel, as shown in the previous slide, devices are connected, each in a separate branch. Effectively, each has its own path from negative to positive. Each has its own circuit, really. So they're unaffected. If each of them have their own circuit, if you open one of the circuits, the other 2 stay closed. So here's the 2 examples, series and parallel. I'll start with series first. So imagine electrons flowing from this end of the battery, right, through this conducting wire, through this first light bulb. Okay, so as you get to this first light bulb, you will have the maximum electromotive force, okay, the highest push and the greatest amperage. As you get through this light bulb, the resistance of the light bulb will lower the push, will lower the voltage to the next light bulb. So you would find that this next light bulb would not be as bright as the first. The third light bulb would be dimmer than the second, so you get a subsequent dimming of the light bulbs as you go down the chain. In a parallel circuit, the advantage is they are all wired in separately, really. And what you've got is you've got each of them. You can trace a path for each of them, back to through the whole thing. So take over here to the second light bulb, nice straight path that doesn't involve the first light bulb. The third light bulb does not have to receive electricity from which has gone through both of these two first light bulbs, right? This light bulb at the end has its own circuit, just like they each have their own circuit. So, in parallel, they will split the total current between all three of them, but they will all receive the same voltage. So while all the light bulbs might not be as bright as one as one of them by itself, they will all be equally as bright as each other. And that'll end this section.